Thank you, and it's a real pleasure to be here. I know it's beautiful outside, and I'm keeping you from going out there, but I will not try to sing to keep you away. Let's see. Nicholas asked me to say something about myself. He said it was a tradition here, and so I'm going to say two things. But after I can get this to work, okay. The first one is when people ask me, what do I do? I say I'm a translational computer scientist. And you might be wondering what that is. And so I have a slide on that. I'm not going to go through this in detail, but this is something that David Abramson from Queensland and I have been trying to define. We got together and say, okay, what is it that we do? And why do we enjoy doing it so much, right? What makes it different? We're not pure computer scientists, maybe not pure engineers, something in between. And so if anybody wants to talk a little more about this, I'd love to talk more about this. The second thing about myself is I'm an almost recovering Fed. And Fed means a federal servant in the United States. And I'm moving up to this institute out here in the University of Utah, the Scientific Computing and Imaging Institute, and I did want to say something about it. It's a great place that looks at, well, translational computer science research, right, and applies it to a bunch of different applications. Again, if you want to know more about this, I'd love to talk more about that as well. But that is not the topic of this talk, and so here's an outline of what I am going to talk about, right? I'm going to talk about urgent computing. This is something that we've been looking at for a few years, along with Danielle, who came to me as a postdoc. Now he's a researcher at INRIA in France. But we've been saying, okay, what are these urgent computing? What defines them? How can they leverage the computing continuum? And then we've been trying to build some tools that might help. Given yesterday's panel, I thought it'd be nice to maybe provide some context here, right? So what's urgent computing, right? What motivates it? And that's really many of the challenges we are seeing where computing data and processing data, which is computing, can play a huge role. And here are just some examples. Most recently, we saw it with Cyclone Gabrielle here that impacted Auckland, right? So there are natural events, man-made events that happen where computing data can assist in being able to make decisions, to act on it, to have strategies to manage these events. And that sort of frames what we call as urgent science, whether it is responding or even doing early warnings around earthquakes and tsunamis, managing traffic, right? Weather and climate, like what we saw, environments, like smart factories, and so on, right? And all of us have examples of what's going on. So in this context, here is a definition of urgent computing, right? Again, there was a question yesterday about what's urgent computing in the panel. So this is one definition, right? It's computing under strict time and quality constraints to support decision making within some desired confidence level, right? So here the key thing is not the fastest. It may not be the highest. It's, okay, what do I need to do to be able to make a decision based on the information I have, right, and the resources I have, right? And so if I look at it at a very high level, a canonical urgent computing workflow might look at, identify some events. You're getting data streams. You might have other kinds of notifications. Define something that triggers a workflow. Using resources, using data, using models, you develop a response, and then you take an action. And this could be a loop, right? So that's one way of looking at it. And clearly, an urgent application needs to react to unforeseen events, right? That's the nature of an urgent event, and to manage very complex cost-benefit trade-offs, right? Is it worth waiting for more data, right? is it worth trying to get more accuracy because I might run out of time, I might not have the resources, or I might use up all my battery on my sensor, right? So I have to make very complex trade-offs to be able to meet these constraints of an urgent workflow, and I have to do it in near real time, right? And this could be exact. How do I steer online on-demand computation based on data? How do I balance the different costs, support urgency constraints? So there are a whole bunch of things that underlie urgent computing. And just to give you a broader context, right, this is part of a broader conversation in the US behind what we're calling the National Strategic Computing Reserve. And just to give you some background here, in spring of 2020, when we were just getting to understand the scale of the pandemic, very organically, a bunch of resource providers from the federal government, from industry, from academia, came together and say, how can we help? And the COVID-19 HPC consortium stood up in, and I'm not exaggerating, about a week, and we were making computing software expertise available to any researcher that wanted to use it. It grew, different countries joined in, it just kept on growing organically, and we had this whole system where researchers would come in and they would get access to resources, to data, to expertise, to tools, and be able to address it, right? And so learning from both the impact of doing that, right? There was a clear impact from these kind of activities on our ability to respond to that event, right? And just the concept that we could do this, right? We could create this and be able to mobilize this in an urgent fashion. There was a interagency study, and they came up with this blueprint, right? That's now working on how one would actually implement it, right? Like we have the oil reserve in the U.S. and the other kinds of the marine reserves. So there are different reserves, right? Can we think about computing? And computing, we mean broadly not just the computers, but resources, algorithms, expertise. How can we do this? And it's a short report, and you can download it from this URL, right? In our research, our immediate use case that we were working on right now is this one, right? And this is based on something that we experience a lot in Utah. It's a valley. You have the inversion coming in, and every time there's a forest fire, wildfire in California, air quality just gets really, really bad, right? And to the extent that it's really unhealthy for the local population. And we've been looking at this, and the thinking is that how can we understand based on data we're getting from the wildfires, based on other data we get from our from the wind patterns and other things, as well as models on air quality that some of the research have developed, can we knit them together so that we can do some sort of an early warning, right? Especially in certain neighborhoods where it is really bad. And number of days with unhealthy air quality can be very high in the summertime, which is a wildfire season in there, right? So how can we mitigate these impacts by being able to leverage this continuum, right? Or this idea of urgent computing, right? And that's where this concept of a computing continuum comes in. And again, I'll go through this quickly because Mona and others yesterday did a wonderful job already defining what it is. And really the motivation behind it is that we're getting this really rich landscape of computing that goes from edge devices to very powerful core clouds and HPC centers to things where we have smart devices in the network, data transfer nodes, smart switches, which provide non-trivial capabilities for processing data, right? And so how can we leverage, and each of them bring different kind of cost benefits, right? For example, core data centers have really large amounts of computing power, but getting the data there, as we heard this morning, can be very, very difficult. We have edge computing, which is very close to the data, can respond immediately, very typically, you have low computational and storage capabilities. Power is always a problem. They tend to be unreliable in connectivity. So there are different issues there. And same thing with in-transit, which is really using the data path, you have different trade-offs there. And so the idea here is, can I really leverage the whole thing in some interesting way? Can I use this entire continuum to run my workflow in a dynamic manner, so I'm using resources to add value as the data moves, right? If I can, if I see congestion, can I leverage resources to maybe downsample the data? Or can I use it to do some immediate inferencing on the data and see whether this is interesting enough to move it to the cloud, right? So I can do interesting things along this continuum so that I'm adding value without having to move all my data to the HPC center, the cloud, or doing everything at the edge, right? And so that's sort of one way of looking at this continuum as a spectrum of resources with different trade-offs, different capabilities and costs that collectively can add value to the action, to the workflow, to the computation that I'm trying to do. Okay? And clearly doing this includes research challenges, and here is just a few of them. Right? If I'm going to use the computing continuum to do urgent computing, here are just a few of them. Right? For example, how do I drive the computation to data? Right? It's, I have these different actions, right? But they're triggered based on data coming in, and I don't know when that's going to happen or what combination of things. So really, I have to be able to trigger what I do, where I do it, based on the data that's coming in. There are uncertainties in the data, in the availability of the data, and the resources. So then how do I try to build that into my computational model where I deal with this uncertainty as a first-class design aspect when I'm putting my solutions together? How do I build applications to manage workflows that really adapt, right? When I mean by adapt, you're adding value as you go, right? There's data, there's computing, but there's always a cost-benefit trade-off, right? Yes, I can do more, there's more computation close by, but I have to move my data, I'm going to lose time, I might lose battery power. So overall, what adds to the utility of what I'm trying to do, right? And that's really how you're trying to do this, and so on, right? And there's a bunch of papers that go into a lot more detail about what these challenges are. But there are clearly a lot of challenges as you're trying to build this kind of urgent workflows leveraging the continuum. Again, this is just building on the same concept, right? You can think about this as having requirements at the application level where I'm composing some set of malleable components that you then have to configure in a way that meets your requirements. And the same thing happens at the infrastructure level as I have different places where I can do computing, right, as I move my data or as I trigger the actions I'm trying to do. And I have to balance these different configurations and different operating points based on what most effectively allows me to achieve my goals, right? And that requires a cross-layer kind of thing, right? I might increase my computational capabilities, or I might reduce my resolution or use a different algorithm, and what is the right trade-off really is something that you only know at runtime. So with that sort of context, I'm going to use the next part of my talk to talk about one project that Daniel and I have been working on for some time, and that's called our Pulsar, right? And it's really trying to build a set of programming abstractions and some runtime system that can help you express what I just said in the slide. How do I build these data-driven workflows for meeting an urgent computing kind of a scenario, right? How do I make sure I can do it in a way that I can trigger these computation based on data in a dynamic way, right? And the system that we've built is called our Pulsar, and I can explain what that name means over a beverage at some point. So basic idea is that we have a notion of data sources where we are getting some data. They're coming in from different sensors. Maybe they're coming in from data archives. They may be coming in from computational models, right? There's a bunch of input data coming in. There's a way that you process the data to find out whether it is interesting or it matches certain criteria, and you could, based on individual data values, but you could also think about statistical characteristics of windows of data, either in space or in time, right? And so be able to react to, what's the average change in the density of cars at an intersection, right? Or what is the average temperature in this area, or the average particle count in this space, right? So you can have different ways of expressing what's interesting in the data, and when you detect something that's interesting, you can take some actions, right? And that means you can trigger something else, you can launch some computations, you can change some system parameters, you can trigger some sensing on another device, right? So you can have a sequence of actions, right? So it's very, very simple. If I collect some data, if I detect a pattern, then do something, right? Very, very simple abstraction. And this is really based on a model that we had proposed a few years back called associative rendezvous. Again, at a very high level, what it is a way of doing rendezvous computations, communications, which are very well understood, but instead of doing them based on names, right? Rendezvous are based on mailboxes or names. You do this on content or strings, right? And matching strings. So when strings match, you do something, right? So basically, we had an idea of messages which had some keywords, right? And then we had a set of rules that say, if there's a match on the keyword, then do something, right? And basically, it would work is that you'd send a message, and there would be a matching of profiles, and it could be with exact matching or partial matching or whatever you want to do it, and then some action was taken. And this whole thing was built on top of a DHT, a distributed hash table that we built that was really indexed by content rather than by keys, right? And again, there's some details in this paper, but that's sort of underlying this whole model in our Pulsar. Rendezvous computations where you send the data with some profile, it matches against interests that are already existing, and based on them, some action is triggered. Okay, very, very simple stuff, right? And so based on this, we can do a lot of things in our Pulsar. For example, we can define event-driven programming where we have resources and data profiles. So every data stream has some descriptor on it using some semantic descriptors, right? From our Pulsar's perspective, is agnostic of what those profiles are, except that they have to match with some interests that already exist in the network, right? And these could be based on the content of the data. They could be based on attributes. It could be based on location, right? And the way the workflows execute is the moment there's a match, you trigger events that might match other profiles, right? So there is this kind of a cascading effect that causes a sequence of actions to happen. And then there's a runtime which makes these trade-offs, right, between configurations, between cost, quality, and different type of things. And there's some examples out here where we could have rules on what data to move or when to move the data. It could say, if based on your battery level, or it could be based on computational power, on the level of data, on the amount of quantities of interest that were detected, right? So you could have different criteria that makes that decision, and we might also make a decision of where the data moves, right? Does it move to a edge or a fog cloud? Does it move all the way to the HPC center or a cloud? Does it move somewhere in the network, right? So you can make a determination of where that data moves, right? And so that's the basic idea that underlies our Pulsar. I'll point to a URL where you can download the software. It runs on typical platforms, right? On ARMS, on Raspberry Pis, but also on your typical GPUs and CPUs, right? So it is out there. There are some tutorials out there that you can play with, right? And so this is work in progress, and this is sort of a maybe a precursor to something Pete will talk about, and Ilka, if he gets here, will talk about, right? So we are going back to our motivating use case. We are actually implementing that. There is the Sage platform that allows us to get data coming in, for example, from smoke detection or using camera imagery. There's a bunch of wildfire real-time data and models that come in from Wi-Fi project that Ilkay leads, and there's a bunch of researchers at Utah, led by Heather Holmes, who are building air quality models, right, that get triggered by these things. And so we can, and the goal here is to issue public warnings based on what we are detecting, right? And so we've been working on this. This is, as I said, a work in progress. They have some initial results, but it is evolving quickly. But there are other things we have done. We did build, using the same model, an early earthquake warning system. And this used a combination of things. It used a combination of sensors. So typically when you have early in earthquake warning systems, you use different kinds of sensors which are good for certain types of earthquakes, right? Seismographs may be good for a certain type of earthquakes. In this case, if they are smaller earthquakes, you can use GPS-type devices for larger earthquakes, right? Here the idea is, can I combine all of them in the network and do this in a way that I can really do a warning that's early enough that I can act on it, right? So it uses a combination of federated learning and sensing, all built on our pulsar to do that. This was published in the AAAI 2020 conference and received the best paper for societal impact, I believe. That was what it was called, right? So it's saying, how do I combine this information along with these models to be able to do this in the network in a timely way? And there are other examples out here. There is that one out there really related to the talk this morning. This is trying to detect, I used to run cyber infrastructure for a large ocean observatory, and we were getting a lot of streaming data from the ocean floor, high definition video data, and not all of it was useful, right? So how do you detect at the edge data that's interesting? Especially, we're most interested in underwater plumes coming out of these underwater volcanoes off the coast of Oregon, and so we were able to do that. This one is also interesting. This was using an edge inferencing model to be able to manage the energy in the smart factory. And so you were able to run a lot of that over there at the edge. And when you needed to, right, when you're getting high errors, you were able to move back and train your model again, right? So this is just some examples. How am I doing for time? Here's another one we did, and I'm showing this because I have some results on this in terms of performance. I thought that might be useful. But this is something we did after Hurricane Sandy. So one of my colleagues there, and he does this, right? He goes with these LiDAR. He's got this a truck that's equipped with all these sensors, and he drives around and looks and images all the infrastructure, right? Bridges, buildings, around. And the idea is that he has a database of models, and he can compare them to see whether there's structural damage, right? And that way you can quickly open up roads and infrastructure where you know there's no structural damage, but where there's doubt, then you need to do more assessment before you open up civil infrastructure. So he works with the DOT and other groups in New Jersey to be able to do that. And we were trying to see, right now he'll drive around, bring these disks, and then mount them up, and then run the data and run his analytics there, right? And we said, okay, can we do something on the truck itself? Sometimes he uses drones, so maybe on the drones that he's using, and really triage the data. Is this worthwhile, or is this clear enough that I don't have to do anything with it, right? And so that's really what this workflow is looking at. Can I make quick decisions at the edge on the structural integrity of these things after a disaster, right? Now, this use case was based on data we had already collected, so it's not live, right? But we were trying to see how you could do this using that. And I think the performance results is then simulating that on the Grid 5000 testbed to be able to see what kind of policies might work, right? For example, what happened if I send everything to the cloud. In this case, we were actually using Amazon, right? And you can see bandwidth it's just the orange is data transfer, so all you're doing is transferring data, and that's not very good. I could do things at the edge, right? But then there are limitations there. But then we looked at more interesting things where I could use a combination of resources on the edge. In this case was a drone, the van, and the cloud, and how can I trade off cost of data movement with the performance, and you get some benefits. In here you can start seeing that we can do reduce the data movement as we learn about that. Same thing, we can start using another knob, which is varying the resolution of the data that we are collecting based on what we are seeing, and that gives us more flexibility. And the final one that you see out here is saying that we have a hard deadline, right? Whatever you can do, you have to do this within this time limit, and the deadline varies, right? And so that's a solid line. And C is how can we make sure that we are within that, and that would mean that you drop some data and you sort of approximate that. And so those are the results here. Again, the paper, which I think there was a reference in the previous slide, goes into more detail. And I forgot to mention that he's injecting some noise into the whole thing where he's trying to vary 3 parameters: the data input size, the bandwidth, and the CPU capacity, to see what a real edge environment would be. Again, there's a little more in the slide there. Finally, to conclude, I think clearly we have the infrastructure with the cloud, with the edge, with in-network devices that we can really do this kind of closing of the loop, these urgent workflows, to be able to react to these scenarios in a data-driven manner. And leveraging the Continuum is really allows us to do that because we can make the right trade-offs and do just-in-time computing as needed. Of course, there are multiple challenges, right? And we've been looking at from a programming perspective, how do I express that? I have one more plug, and this is for a workshop on urgent analytics that Daniel is putting together at Europar, and with that, let me conclude. Thank you very much. You can find the software there, and